Comparison between transport coefficients. The coefficient of viscosity of helium gas at 273 Kelvin and 1 atmosphere is eta 1. That of argon gas is eta 2. The atomic weights of these monatomic gases are mu1 and mu2 respectively. Part A. What is the ratio sigma 2 over sigma 1 of the argon-argon atom total scattering cross-section sigma 2 as compared to that of the helium-helium atom total scattering cross-section sigma 1? The viscosity is related to the mean free path according to elementary kinetic theory 1 over 3 n v bar ml. So n is number per volume, v bar is the mean speed, m is mass of one atom, and l is the mean free path. And if we substitute for L 1 over square root 2 n sigma, where sigma is the total scattering cross-section, we find that it is 1 over square root 6 square root mkt. So now this is the first type, m1 kt square root divided by the total scattering cross-section sigma 1. And the mass of one molecule, or one atom in this case, is the molecular mass divided by Avogadro's number. Okay. Now, the viscosity of the second type is 1 over 3 nv bar ml. Again, this will be equal to 1 over square root 6 square root m2 kt. m2 kt, they have the same temperature, 273 Kelvin, and different total scattering cross sections. So it is sigma 2. So this will be equal to m2 L2. This will be equal to m1 L1. And this is n1 v1. This is n2 v2. Okay, now if I look at the ratio eta 1 over eta 2 ratio, the ratio of the viscosities, it is going to be, because mass is equal to mu divided by Avogadro's number, so this here I substitute mu1 divided by Avogadro's number, so I will have in the ratio mu1 over mu2 square root, and then when I take the ratio of eta 1 to eta 2, sigma 2 will go up, so this will be sigma 2 over sigma 1, the ratio of the total scattering cross sections. So we obtain the final answer when we isolate sigma 2 over sigma 1. Sigma 2 over sigma 1 is eta 1 over eta 2 square root of mu 2 over mu 1. All right, so here sigma 2 over sigma 1 is eta 1 over eta 2, and this goes to the left as reciprocal, so square root mu 2 over mu 1. So that's our final answer for part A. Part B, what is the ratio of the thermal conductivities kappa 2 over kappa 1 of the thermal conductivity kappa 2 of argon gas compared to the thermal conductivity kappa 1 of helium gas when they're at the same temperature, 273 Kelvin? Okay, now the thermal conductivity according to the elementary kinetic theory is given by 1 over 3 number per volume n1, the mean speed v1 bar, the heat capacity per atom or per molecule times the mean free path. And at the same time we have the viscosity eta 1 given by 1 over 3 n1 v1 bar M1 L1, so the total scattering cross section. So this gives me the ratio kappa 1 over eta 1 to be C, this is of course C1, C1 over M1. Now this is C1, heat capacity per atom. M1 is the mass of 1 mole divided by Avogadro's number, that is the atomic weight divided by Avogadro's number. And this Avogadro's number goes upstairs. Heat capacity per molecule multiplied by the Avogadro's number gives us the molar specific heat, CV, divided by mu1, because the volume is constant here. And also note that CV is equal to 3 over 2R for monatomic gases. Okay, so similarly, if I do the same calculation for kappa 2 over eta 2, therefore I would obtain the CV1, this is going to be CV2 divided by mu2, but CV1 and CV2 are the same, 3 over 2R. So if I take the ratio kappa 2 over eta 2 divided by kappa 1 over eta 1, or eta 1 multiplied by eta 1 over kappa 1. This is CV multiplied by the CV values are the same, so CV over mu2 for kappa 2 over eta 2, and for kappa 1 over eta 1 I have CV over mu1, but mu1 goes upstairs, so this will be mu1 divided by CV. They have the same CV value, so they cancel. So here I obtain the ratio mu1 over mu2. So if I isolate kappa 2 over kappa 1, this will be equal to eta 2 over eta 1. When it goes here, it will be reciprocated. Eta 2 over eta 1 multiplied by mu1 over mu2. So that's the answer to part B. Part C, what is the ratio d2 over d1 of the diffusion coefficients of these gases at the same temperature, 273 Kelvin? Now the diffusivity d1 is 1 over 3, according to elementary kinetic theory, v1 bar multiplied by L1. So if I divide this by the coefficient of viscosity, eta 1, which is 1 over 3 N1 V1 bar M1 L1, we find that the ratio is diffusivity divided by viscosity. It's going to be, because these 1 over 3's will cancel and V1 bar L1 will cancel, it will be 1 over N1 M1. Now, what is 1 over N1 M1? Now this is the number of molecules per volume. Mass of one molecule, mass times the number gives us the total mass divided by the volume. So this is going to be the density, rho 1. So 1 over rho 1. So if I take the ratio diffusivity 2 over diffusivity 1, it will be the ratio of diffusivity 2 over diffusivity 1 will have the so let's write here diffusivity 2 over eta 2 will be equal to 1 over rho 2, similarly. So when I take the ratio of these two, diffusivity 2 over diffusivity 1 will have rho 2 on top, and eta 2 will go on top. So we will have eta 2 over eta 1. So diffusivity 2 over diffusivity 1 multiplied with eta 2 over eta 1. So let's do this right here. Take the ratio. Diffusivity 1 over eta 1 multiplied by eta 2 over diffusivity 2 will give us rho 2 over rho 1. So you can see that d2 over d1 will be eta 2 over eta 1 multiplied with rho 1 over rho 2. So this will go here as rho 1 over rho 2, and this will be d2 over d1. So at the same time, the density is basically total mass divided by the volume. So the mass of 1 mole is basically the molecular mass. So let's say that we have 1 mole and we have the same volume. Then this will give us, for the final answer, eta 2 over eta 1 multiplied by mu 1 over mu 2. Why? Because rho 1 is Avogadro's number, let's say 1 mole, times mu 1, the total mass, divided by the volume occupied. So if we have 1 mole of these gases, you can see that it's going to be also mu 1 over mu 2. Alright, so this will be our final answer for the ratio of the diffusivities. Eta 2 over eta 1, mu 1 over mu 2. Now, the number of moles in these two gases are equal because we have the ideal gas law, P bar V is equal to nKT. The temperature is the same, the pressure is the same. So we have 273 Kelvin and 1 atmosphere. So you can see that we have, if the volumes are the same, then the number of moles will be the same. So we have n's are equal for these two gases. So normally this would be equal to number of moles N1 times Na mu 1 over V, but N1 is equal to N2. All right. So that's the answer to part C. Part D, the atomic weights of helium and argon are respectively mu1 equals 4, mu2 equals 40. The measured viscosities at 272 Kelvin are 273 Kelvin are respectively eta 1 equals 1.87 10 to minus 4 and eta 2 equals 2.105 10 to minus 4 grams per centimeter per second. Use this information to calculate approximate values of the cross sections sigma 1 and sigma 2. Now we will substitute these results. Mu 1 is equal to 4, mu 2 is equal to 40. We have coefficient of viscosity 1.87 times 10 to minus 4 grams per centimeter per second, and the second coefficient 2.105 times 10 to minus 4 grams per centimeter per second. So the total scattering cross section sigma 1 is equal to, from part A, m1 kt square root divided by square root 6 times the coefficient of viscosity eta 1. So if we substitute that here, we will obtain, for mass of one molecule, we have 4 divided by Avogadro's number, 6.02 10 to 23. We have Kt value 1.38 10 to minus 16 times 273 Kelvin. Then we have square root and square root 6 and eta 1, 1.87 times 10 to minus 4. And this gives us, for the total scattering cross-section, sigma 1, 1.13 times 10 to minus 15 centimeter square. And we do the same calculation for sigma 2. Sigma 2 is, we have the ratio here, sigma 2 over sigma 1 is eta 1 over eta 2, square root mu 2 over mu 1. So sigma 2 is sigma 1 times eta 1 over eta 2, because it was eta 1 over eta 2 here. And then square root mu 2 over mu 1, square root mu 2 over mu 1. So this is a sigma 1 value, 1.13 times 10 to minus 15, multiplied with eta 1 over eta 2, eta 1 over eta 2, 1.87 10 to minus 4 divided by 2.105 10 to minus 4, square root of mu 2 over v1, 40 over 4 square root. So we obtain sigma 2, 3.16 times 10 to minus 15 centimeter square. Part E. If the atoms are assumed to scatter like hard spheres, estimate the diameter d1 of a helium atom and the diameter d2 of an argon atom. Now, the total scattering cross-section is pi diameter square, or 4 pi r square, remember. So we have diameter 1 is sigma 1 divided by pi square root, which is 1.13 times 10 to minus 5 divided by pi square root. And this gives us, for the first diameter, 1.89 10 to minus 8 centimeters. And for the second one, d2, we have sigma 2 over pi square root. This is now 3.16 times 10 to minus 15. So this was 10 to minus 15. Divided by pi square root. And that gives us, for d2, 3.16 times 10 to minus 8 centimeters. So we have been assuming these diameters of 10 to minus 8 centimeters. You can see that order of magnitude, it is correct. Okay, so we're comparing transport coefficients. We have the first type, argon gas. The first type is helium gas. The second type is argon gas. They have the same temperature and pressure. And we know their monatomic gases and atomic weights are mu1 and mu2. First, to calculate the ratio of the total scattering cross-sections knowing the viscosities, we use the result of elementary kinetic theory, 1/3 mv bar ml, and substituting for L, 1 over square root 2 and sigma, and values cancel, and for V bar we substitute square root 3 kT over m, and this gives us our familiar result 1 over square root 6 square root mkt over sigma. So the ratio of the viscosities eta 1 over eta 2 is square root m1 over m2 sigma 2 over sigma 1. But m, mass of one atom, is the atomic weight divided by Avogadro's number, so it is actually mu1 over mu2 square root mu1 over mu2 sigma 2 over sigma 1. So sigma 2 over sigma 1 argon to helium ratio is then eta 1 over eta 2 square root mu2 over mu1. That's the answer to part A. Now in part B, we're asking the ratio of the thermal conductivities. The thermal conductivity is 1/3 NV bar Cl, where C is the heat capacity per atom. And then we have the viscosity. If we take the ratio, the ratio is C over M. M is the molecular weight divided by Avogadro's number. So we obtain the Avogadro's number multiplied by C, giving us the heat, the molar specific heat, CV, for a constant volume, divided by mu, mu1. Then we have, or if we have constant pressure, this would be Cp, which is 5 over 2R, but the answer doesn't change, right? So it's going to be the same C values for the two monatomic gases. So you can use CV if it's constant volume or Cp if it's constant pressure. Well, here actually it is constant pressure, so we could use Cp. Now, kappa 2 over eta 2 is Cv2 over mu2 in that case for constant volume. So we have the ratio kappa 2 over eta 2 multiplied by eta 1 over kappa 1 is Cv2 over mu2 multiplied by mu1 over Cv1, but they have the same heat capacity, molar specific heat, so they cancel. 5 over 2R or 3 over 2R, it doesn't matter. So we have mu1 over mu2, so kappa 2 over kappa 1 becomes eta 2 over eta 1, mu1 over mu2. Part C, what is the ratio of the diffusion coefficients? 1/3 V bar V bar L is the diffusivity. If we take the ratio with respect to the coefficient of viscosity, the ratio is 1 over Nm, where N is number per volume, M is the mass of one atom, so number multiplied by the mass of one atom gives us total mass per volume, that is density. So we can see that if I take the ratio d1 over eta 1 to d2 over eta 2, d1 over eta 1 multiplied by eta 2 over d2 will give me 1 over rho 1 multiplied with rho 2. So d2 over d1 in that case will be eta 2 over eta 1 rho 1 over rho 2. So the ratio of the densities. So if we have the same pressure and same temperature, the number per volume, the number of moles per volume will be the same. So we can use the same number of moles, N1 equals N2. Then you would have, for the density, number of moles of Avogadro's number, mu, divided by, so let's see here, this is the mass of 1 mole. If you multiply it by N, you get the total mass divided by the volume V. You will have the density, right? So it's going to be a mass of 1 mole, number of moles, that's the total mass divided by the volume. So rho is equal to mu n over V. If you want to calculate mass of one molecule or one atom, it would be mu divided by Avogadro's number Na. Okay, so with that, for rho 1 over rho 2, I can substitute mu1 over mu2 if they have the same n divided by v value. So you can see that n divided by v value n1 over v1 is equal to n2 over v2. So we have the same n over v values. Therefore, it is mu1 over mu2. Now, in part D, we have the atomic masses, atomic weights, 4 and 40, and we have the measured viscosities. We use this information to calculate the total scattering cross-section. The first one is square root m1 kt over square root sigma eta 1. So this basically we have obtained here eta 1 square root 6 sigma 1 is equal to square root mkt. So it's square root mkt divided by square root 6 eta 1 would be equal to sigma 1. That's what we do here, and we obtain 1.13 10 to minus 15 centimeters square. Now the ratio sigma 2 over sigma 1 ratio, eta 1 over eta 2, square root mu 2 over mu 1. So if we substitute for sigma 1 our result, eta 1 and eta 2 values were measured. We substitute that here, square root mu 2 over mu 1, 40 over 4. We obtain sigma 2. In part E, if we assume that they are scattering like hard spheres, what should be the diameter of a helium atom and of an argon atom? D is equal to square root sigma over pi, because that's the definition of total scattering cross-section. So if we substitute the numbers here, we obtain 1.89 10 to minus 8 centimeters and 3.16 10 to minus 8 centimeters. So 1.89 is for helium and 3.16 is 10 to minus 8 centimeters is for the argon atom.